All right, so I'd like to welcome everybody to this GeoFlow meeting. For those who are new, GeoFlow is a collaboration between different institutions, theorists and experimentalists, condensed matter, quantum computer builders, and quantum gravity people. And we've been having a lot of fun with these meetings, so welcome. And I'm gonna hand it over to the organizers of this meeting, particularly Xiao Liang, who's been leading. And I'd also like to thank, I'd like to thank him as well as Norm, Yao, and Paolo Glorioso, who helped a lot, as well as my own postdocs, Hugo and Masamichi, who've been all putting this together. So with that, I'd like to hand it over to Xiaoliang.
Yes, thanks, Raphael, for starting the meeting. I just want to briefly say that so we planned 45 minutes for every talk, and that include 10 to 15 minutes of questions. So please, yeah, for the speakers, please plan your talk to be around 30 to 35 minutes. It doesn't mean it has to be 30 minutes plus the 15 minutes of questions afterwards. It could be, I mean, I encourage everyone to just ask questions in the middle. If you have a question, feel free to speak up. If we have a lot of questions in the middle, it's okay. We don't have to have a Q&A session in the end, but keep in mind the total is 45 minutes. I appreciate if you keep the time. And for during the breaks and during the poster session in the afternoon, we will have we'll have a breakout room we'll have this gather town room. So hopefully you can see that you can discuss the posters there, and also we can have other more informal discussions. If you haven't used gather town before, just remember you need to use the arrow buttons, the up, down, left, right on your keyboard to move you around in that virtual room. I think that's the only non-trivial thing you need to know. Okay, yeah, so thanks for all our speakers. Look forward for the talks and discussion today. So then Hugo will chair the first session.
Sounds good. Thank you very much, Xiaoliang. Thank you, Raphael. And yeah, so let's get started. So our first speaker is Avikar Periwal from Stanford. He's going to tell us about programmable interactions, emergent geometry, and array of atomic ensembles. So thank you, Avikar.
Yeah, hi everyone. I'm Avikar, and I'm going to talk about some of the recent work in the Schleyer-Smith group on these programmable interactions and the emergent geometry we see in an array of atomic ensembles. So probably everyone here has tried to simulate a quantum system in some way, shape, or form. But for a system with, a large number of degrees of freedom, this just isn't possible on a classical computer. You can play various games to try to do better, but you have to make some assumptions then. So just generically, these computations aren't possible because our Hilbert space is increasing in size exponentially. So if we want to look at quantum systems and sort of simulate them in some capacity, there's sort of a variety of things that we need. So the first is clearly we need some sort of scalability. It doesn't make sense to have things grow exponentially. But also you need some addressability. You want to be able to measure any observable that you want. And you also want to be able to maybe prepare sort of arbitrary initial states to look at. And also you need programmability. So ideally you just enter in some Hamiltonian, on a classical computer, you just type in your numbers for your matrix and run your simulation. So you want to be able to do ideally the same thing on your quantum mechanical platform. And so there's sort of a variety of different experimental techniques that people are using to try to probe the quantum mechanics. So the first thing that we can mention is superconducting qubits. I'm sure you've all heard about Google's quantum supremacy claims. And here, each qubit has to be fabricated and connected. But if you want to increase a qubit, you're not doubling your system size. You just have to fabricate a new one and wire the connections between the two. But there's some problems here where one, the qubits you want them to sort of be the same, but you have to fabricate all of these to be the same. And you need to make physical connections between all the qubits. And then because we don't know how to do high temperature superconducting yet, you need to put these in dilution refrigerators and connect all these wires coming out. So, you know, even Google set up a processor with 54 qubits, and in the end, they only had 53 to work with. So you can ask, okay, well, you could look at sort of naturally quantum mechanical objects. So in ion traps, for example, the ions are all the same by default, and then they act as your quantum degrees of freedom, and you can trap them using their electric charge. And ion traps have really good sort of single qubit readout and fidelity of rotations. And this has been used to generate, for example, a thermofield double state in the Monroe group. But there's some problems with ion traps. If you want to, say, trap them in 2 dimensions or really increase the size of your chain, there's some limits to what you can do with these electromagnetic traps. And so to that end, you can look at, let's say, neutral atoms. So neutral atoms can be trapped just using optical forces, so just using like well-focused laser beams, or they can be trapped in, say, an optical lattice with some cross-propagating beams. That's what's shown on the bottom. On the top are individually imaged atoms in a tweezer array. And so this scales really nicely because the first order, the only thing you need to add more qubits is more laser power to generate another trap. And also because you can image all of these individually, you have access to all these local degrees of freedom. And so recent measurements out of Harvard, for example, have these neutral atom arrays with more than 200 degrees of freedom. But really, I've only talked about scalability and addressability here. The real issue, especially in neutral atoms, is how do we program them? Neutral atoms aren't going to interact by default. And so what you can do is put them, say, in an optical lattice, and where they hop around and have interactions mediated that way. And you can maybe try to program the geometry of the lattice by tuning the geometry of your optical laser beams. You can try to induce also maybe sort of more distance dependent profiles by exciting atoms to high-lying electron states, these Rydberg levels. But that's still going to give you some interaction profile that decays with distance. And so what we want to look at is how can we really directly program the connectivity matrix between different quantum degrees of freedom? How do we increase the control in neutral atoms beyond that? And if we could control this matrix, what sort of things could we look at? So the first is if you just imagine controlling the signs of your interactions in, say, in some lattice system, then you can start to probe spin glass physics or frustrated systems. If you say, let's control the phase of the interactions at a phase to a hopping term, then you can start to maybe probe physics of artificial gauge fields or topological systems. And now both of these are still on just 2-dimensional lattices. Well, if you can program your connectivity matrix arbitrarily, you can change the geometry however you want, and maybe you can start to study models of quantum gravity, which is something we're going to look at later in the talk. So just to go over roughly what we're going to talk about, I'm going to talk a little about the experimental apparatus that we use, our actual cavity. I'm going to show how we use the cavity to generate interactions at arbitrary length scales. And then we're going to use multiple interactions to generate exotic geometries. And then finally, we're going to look at some holographically inspired spin models. So this is a schematic of our apparatus. We have 2 really nice mirrors that generate a single mode optical cavity. And we have underneath a very nice lens that we use to generate these tightly focused micro traps, which have maybe 10,000 rubidium atoms in each one. So we're going to treat each of these as a classical spin. And so this lens gives you sort of the addressability on each site. We can image each site directly. And if we drive photons, send photons into the cavity, depending on how we choose to do that, we can sort of start to program the interactions a little bit. So one thing I want to be really clear is we can't image these individual atoms. We're just treating them as classical spins, these groups, these ensembles of 10,000 plus atoms. Okay, so in terms of programmability, what's already been done in cavity systems. So last year, what we were working on is changing the magnetic field that the atoms were experiencing relative to the propagation of the, changing the angle of the magnetic field that the atoms were feeling, and that tuned the interaction type, tuned the anisotropy of a Heisenberg model. So going from completely an XY model all the way to completely an Ising model. And that actually tunes between sort of chaotic and integrable points, looking at the dynamics. And that's theory work done by Greg and Ehud Dalton. In the Lev lab, so one building over from us, they coupled multiple modes of an optical cavity to their atoms, and they can use the interference in these multiple modes to generate some really interesting sign-changing, distance-dependent interaction profiles. But for us, how are we going to probe the interaction? So we have on these sites rubidium atoms. We're going to treat our spin states as the f=1 hyperfine manifold. So each atom's a spin 1 system, and we're going to initialize them all in the MF=0 state. And so the cavity mediates an interaction where two atoms in the MF=0 state can be excited and then decay into the side modes. So into the MF=+1, -1 states. And so there's a F+, F- at different sites, and there's some coupling between them, Jij. And our goal today is to tune the Jij however we want.
Avikar, can I ask actually just a quick clarifying question? I just want to make sure nobody was confused by this. So you made a comment earlier about treating these as classical spins, but actually this is a process driven by quantum fluctuations, right? So
yes.
Do you want to like maybe reconcile? So they're large, but actually the quantum mechanics is playing a role, right?
Yes.
It's maybe important to make clear.
So these are not happening on a like per site level. This is happening on the individual atoms in each site. Okay, so naturally the single mode cavity is going to mediate interactions between any two pairs of atoms, which is just going to look like interactions between any two sites. There's nothing breaking the symmetry. That each atom can talk equally to the single mode cavity, and so you have a connectivity graph that's completely connected. And so if we want to measure these interactions, what we can do is turn on the drive, let some atoms move into the side modes and take a picture of the populations in each state. So we have 18 traps here, and we can look at, say, the population of the -1 atoms in one site and the population of the +1 atoms on another site. And there's, n squared choices and n squared combinations. And we can look at the correlation matrix between every position, and everything's connected. So I just want to say this is real data, not simulated or anything. This is you can really see every site's interacting with every other site, or atoms on every site are interacting with atoms on every other site. And so if we want to control this, the first sort of natural question is how do we localize these interactions? How do we confine them to a single site? And so the magnetic field sets the energy splitting between the different levels of the spin system. So if we introduce a magnetic field gradient across these sites, then there's a difference in energy splitting for each site. And now if you have some pair of atoms that's trying to pair create, it can only happen on a single site because it's not energetically possible to have one atom hop to a different energy than the other. And so when we just turn on a gradient and repeat the same measurement, all these correlations are localized onto the site where they live. And so once we've localized things, we can ask, well, can we selectively reintroduce couplings? And to that end, all we're going to do is just add in photons to bridge that energy gap. So instead of having just this one drive field, there's additional photons that allow you to bridge that energy gap. So say, as a concrete example, we look at a distance of 10 sites. So then we need to introduce photons that are at an increased or decreased energy that corresponds to 10 times the gradient. And so in frequency space, we're sending in two sets of drive fields, and they're going to, because the energy splitting in frequency space is small compared to the actual optical frequency we're sending in, it's just going to look like a beat note where we're modulating the amplitude as a function of frequency. And so when we just drive the cavity with a modulated amplitude with a frequency of 10 times the gradient per site, we generate interactions at a distance of 10 sites. So there's these strong correlations at plus minus 10. And then just our gradient is linear. So that gives us a translationally invariant system. And if we want to just, if we want to look at the profile of interactions as a function of distance, we can just average along the diagonals. And when we do that, there's sort of clear peaks at plus minus 10. It's the same thing we're looking at here. But this is sort of a one-dimensional plot that gives you profile of interaction as a function of distance. And so now we can vary the frequency and see how these peaks move. And sort of as we might expect, we have sort of exact control over which sites are interacting just by specifying the amplitude modulation frequency on our waveform. So really the frequency spectrum of the drive amplitude is going to specify the distances at which things are interacting. And now we can zoom in on, say, sites 9 through 11 and look at what happens when we drive at non-integer multiples of the gradient. And really these interactions only happen when the appropriate sort of energy conservation conditions are met.
Sorry, why is the picture on the right side? Why is it why it's not a line, but there's a breaks between them?
So here you're modulating the drive field at, say, so we have like 18 discrete sites, and you're modulating at a frequency that corresponds to like 9.5 sites. So there's no atoms to really have the pair creation there.
Okay. Thanks.
Okay, so if we look at this plot a little more closely, you can see, say, at distance 2, there's actually a whole cascade of peaks at multiples of 2. And the same thing at distance 3 and distance 2 times 4 and so on. And so we wanted to understand, is this a spreading thing? Because we worked reasonably hard to make sure that the dry field actually didn't have any harmonics. So if we look at we do a rotation and measure the spin correlations on different sites in the X basis, which gives us better signal to noise. We can see that there's sort of an overall growth in correlations, which we expect. But also there's sort of a spreading moving out. So we have started interactions at distance 3, and then interactions at distance 6 slowly grow out all the way to say 12 here. And when we look at this, these measurements in momentum space, we can see that the momentum mode, the 2 pi over 3 momentum mode, so corresponding to a sort of full rotation after 3 sites, that's growing really geometrically as a function of time. And so to understand what's happening here, we're going to look at a slightly different picture. So this is a drive form for, say, interactions at a distance of 5. So 5 times the gradient per site is the frequency. And we'll say initially, all the spins will be aligned. And now a spin in a magnetic field is just going to be rotating at some Larmor frequency. But because we have a gradient, they're all going to be rotating at different rates. And so if we're going to reference, sorry, this is the time t equals 0. We're going to reference to the sort of site 0, the first site, and say that one's not moving. And now if we look at what the spins look like after 1/5 of a block period at the peak of the first peak, you can see they're sort of aligned at every distance of 5. And if we look at every continual peak, they're always aligned at a distance of 5 and 10 and 15. And really, because our magnetic field gradient is linear, we're just at every given time, you're looking at something that's close to a momentum mode. And the probe is just going to amplify whatever spin texture it sees at that time. So in this case of frequency 5, it's always going to be, was there a question? All right, it's always going to be high when the spins are aligned at distance 5. We can ask, okay, well, what if we only drive at points where the momentum mode is well-defined? So just generically, at any given time, it's not going to be well-defined because there's sort of a finite system. But there's times every sort of 18th of the block period with 18 spins where the momentum mode will be well-defined. So what does that look like? It's just the sort of modulated waveform, but we apply a mask, a Dirac comb, and on top of it. And we drive it like this. Instead of seeing interactions just at a fixed distance, there's interactions at some distance and then 18 minus that distance. So for 3, for example, you have interactions between sites 0 and 3, but then you also you add interactions between distance 0 and 15. And really the way to think about this now is not as long interactions on a chain, but as sort of the same interactions on a ring, right? We have periodic boundary conditions. So even though the system is still this one-dimensional chain, the interactions are happening on an effective ring. And just to go over one more time, sort of why this happens, if we look in the frequency space, if we look at a single modulation, we just generate interactions at a fixed distance. So for the case of 5, we generate interactions at a distance of 5. Here we have a Dirac comb multiplied in time space with the same modulation, which means in frequency space, there's some convolution of a Dirac comb, and that gives you peaks at, say, 5, but then also the Dirac comb frequency minus 5, the comb frequency, then so 18 plus 5, and so on. But the atoms are only going to really interact with the components of the field, with the components of the spectrum that are smaller than 18 sites. So the only ones that they're going to pay attention to sort of are distance 5 and 18 minus 5. All these higher components are ignored. So let's try to look at how can we show that I told you this is a ring, but let's try to look at this this geometry without any sort of assumptions about what's going on. So what we can do is look at sort of a very simple case, nearest neighbor correlations with periodic boundary conditions. And we can just look at correlations as a function of distance. They sort of decay, and then there's a wiggle due to basically probably experimental imperfections, and then this increase in strength as you have the periodic boundary conditions. And we can make an ansatz that the interactions decay sort of in a Gaussian fashion. And if you do that, you have some sort of effective distance between sites as a function of physical distance. And if we say want to generate some set of coordinates that the sites should live in, well, we have n squared distances or order n squared distances between each set of points, and we only have n by dimension coordinates. It's over constrained. We can just solve this. And so when we do that,
why is it Gaussian?
So I think we don't have like a sort of very fully analytic form right now. Our initial guess was like a thermal state, but I think it's a function of this pair creation process, which is sort of amplifying specific modes. So it's not quite generating a thermal state. And that's it's sort of consistent with our like truncated Wigner simulations. Yeah.
Maybe
usually it's and most of the case the correlation function goes like exponential rather than Gaussian.
Yeah. So that was what we tried at first, and it seems to work also reasonably well, but it wasn't really consistent with our simulations.
Maybe I can add a comment to that. So in some limit, we're not fully in this limit, but in some limit where you have kind of an effective Floquet Hamiltonian if you modulate quickly enough. Mm-hmm. There's essentially a growth rate in momentum space of these different momentum modes that is set by basically the intensity of this drive waveform. So actually the drive waveform is a dispersion relation. And it turns out with this pair creation physics, there's actually an exponential growth rate, which is proportional also to the intensity of this drive waveform. So there's some kind of a quadratic peak. Okay. And it seems sensible that because you have this exponential growth, but the growth rate is quadratic, that it should be a Gaussian. That's roughly where I think this is coming from.
I see.
Yeah.
Thanks. Okay. Okay.
Okay. So we can just generate some set of coordinates and then draw in actually every edge. So every edge corresponds to an element in the correlation matrix, so the sort of n squared matrix. And actually, if you look closely, each edge is drawn in this plot. So maybe there's you can see faintly the 0 to 14 edge, for example, but the opacity of each edge is set by sort of an inferred interaction strength, which just comes from the inverse correlation matrix. So in this way, we can visualize the geometry directly from measurements. We're not making any assumptions about the system or the drive or what we're putting in. Both the coordinates and the connections come directly from the correlation matrix. And so now we can look at this in a number of examples. So sort of the simplest case is to say, look at interactions at a distance of 3. You sort of expect 3 chains that are disjoint because you don't have any interactions between nearest neighbors and next nearest neighbors. And so when we sort of extract our geometry of the same effect. But we can do this again on sort of even more complicated waveforms. And so we can actually generate interactions of opposite signs on different legs. So this is a cylinder, which is wrapping up. We have interactions that are anti-ferromagnetic, so anti-correlated at nearest neighbors, and interactions that are correlated, so ferromagnetic interactions along distance of 6. And we do that by having interactions at a distance of 6 and interactions at a distance of 1, so 2 waveforms, adding them up, but we change the relative phase between the two. And that sets the sign of the interaction. And so we can actually put sort of all 3 things that we've talked about together with multiple frequencies and with multiple frequencies and periodic boundary conditions. And so if we have nearest neighbor interactions that are ferromagnetic and interactions at a distance of 9 that are anti-ferromagnetic, so we have basically this ring and we're connecting directly across the ring. Then when we try to extract the geometry, we get a Mobius strip. And so if you look at site 0, it connects to 1, 2, wraps around to 8, but at 8, it crosses over, the interactions cross over to site 9, and then they're continue looping around to site 17, and then cross back to 0. So there's just one single edge. And the width of this Mobius strip is spanned by these anti-ferromagnetic interactions at a distance of 9. So again, this is extracted without any assumptions about the interaction profile you're putting in. So if I just showed you the correlation matrix, it's sort of the natural geometry that you would say that the sites are interacting in. Okay, so these are all just looking at, representations in Euclidean space. What if we want to move on and look at sort of systems with maybe some curvature or something like that? So we can look at sort of gravity-inspired systems. So gravity might be continuous and our system's discrete. If we want to look at a quantum system with gravity, we'd sort of naturally maybe turn to the ADS-CFT correspondence. And so we want maybe some sort of discretized version of this. And just on a physical level, it's not necessarily clear that gravity should be continuous. You maybe want some sort of discrete model, right? Like the Planck length is a finite quantity, for example. And so what we're going to look at is p-adic ADS-CFT. So there's sort of a number of different discretizations here, but this is one that preserves sort of the symmetries of the system. So here what happens is the gravitational bulk, it corresponds to this Brouillard-Titz tree. It's just a sort of binary tree in the case of p equals 2. And the leaves of this tree correspond to the boundary of the system. So this is, this preserves sort of the symmetries in ways that some of the tensor network models maybe don't. And to that end, we're going to look at sort of this p-adic inspired spin model, which has interactions at distances that are powers of 2. So we have interactions at distance 1, 2, 4, and so on, and no interactions at other distances. And the strength of the interactions is going to be set by this S parameter, and that's going to tune between a non-local and a local geometry. So in the S equals -1 case, the negative S case, we have stronger interactions at nearer neighbors. And as you go to each successive power of 2 in distance, the relative strength of the interaction decreases by a factor of 2 for S equals 1. If we look at S equals 1, we have the sort of opposite approach. The most non-local set of interactions is the strongest, and as you move closer and closer to the initial spin, the strength of the interaction decreases by a power of 2. So in the S=1 case, this non-local case, the appropriate way to think about these spins is really as living on the leaves of this binary tree. And so, you have interactions between 0 and 4, and those two sites should therefore be closer because those are the strongest. That's the strongest set of interactions. And now if we want to look at, say, distance on this tree, instead of looking at a real norm, you look at the corresponding p-adic norm, which is just 1 over the biggest shared power of the biggest power of 2 in that representation. So for example, with sites 1 and 5, their real distance is 4, but their p-adic distance is going to be 1/4, because that's the biggest power of 2. With a distance of 6, the corresponding p-adic distance is 1/2, because the biggest power of 2 and 6 is 2. And this is an ultrametric norm. It's not Archimedean. So that is to say that if we have any 2 points, the distance between those 2 points is less than the distance between either of those points and any other point. Another way of saying that is that any triangle that you draw in this geometry is isosceles. Okay, so we're really trying to move away from the sort of Euclidean Archimedean. And now I said we can tune S, and S sort of tunes geometry. So in S=1, we have this sort of tree-like structure. At S=-1, that's very local interactions. We can really just think of this as a chain or a ring. There's nothing there. There's the dominant interactions are just the nearest neighbor ones. And now if we sort of, the next natural question I think is, well, what happens at sort of the inflection point when you tune between these two? And sort of some work from Greg suggests that it's a fast scrambler, where there's not really a sense of locality. And so one thing I just want to mention is the ordering in these sites is in the non-local case is not the same as in the local case. And the transformation between these two is the so-called monomap, which just reverses the binary representation of the number. So in a physical sort of ordering, in the Archimedean ordering, you'd go from 0 through 4, and 4 would say be 1, 0, 0. If we just reverse that 0, 0, 1, again, that gets mapped to position 1 in the non-local case. Okay, so let's look at some actual measurements. So we're going to start with this local S=-1 case. And here the correlations decay really smoothly with distance. If you looked at this, you say, okay, this is an appropriate metric, the Archimedean metrics, reasonable. And now, I mean, the interesting part is when we can do really non-local things, and you see peaks at a distance of 8, a distance of 4, a distance of 2, with sort of decreasing strengths. And if you just look at the correlations as a function of distance, there's no one would say that the Archimedean metric is really an appropriate one. So what we can do is look at these correlation plots and monomap the X and Y axes, right? So put them in sort of the order we expect. And there you can see blocks of 2, blocks of 4, and then blocks of 8, which correspond to interactions at a distance of 8, 4, and 2 sites, respectively. And you can really start to see the structure in the system that's maybe not apparent when you look in the physical ordering of sites. And indeed, when we now instead of mapping versus the Archimedean distance, we look versus the sort of 2-adic norm, the correlations as a function of distance really decay smoothly. And now one sort of final thing, we were able to reconstruct the geometry of sort of the Euclidean systems just by looking at the correlations. And looking at the correlations and mapping them in some way, we were able to see that they really should have the information of the tree, right? Like everything we said about the tree makes more sense when you look at the non-local correlations. So can we sort of reconstruct the bulk from these correlations? And to that degree, what we're going to do is just generate a set of coordinates in the same way we did before, but we're not going to draw connections in the same way because we're looking for something else. So what we do is
so just maybe you have like 2 minutes,
okay.
You know, something between 2 minutes and 5 minutes. Yeah.
Okay. Yeah. So what we're just going to do is coarse grain and draw connections, and so when you do that, this tree shows up, and we can try to do the same thing in the non-local case, and immediately you sort of see we have this ring structure, and there's no sort of bulk to speak of. And so I mentioned that S equals 0 is a fast scrambler. We can sort of start to move towards that by measuring sort of proxies for entanglement entropy. We can't actually measure entanglement entropy. And so we can just cut our system in half and look at the correlations on sort of either side. And as we tune from local to tree-like, the correlations increase in the physical ordering. If we look instead at the monomapped ordering, they decrease as a function of non-locality. And then we can ask, okay, what's the optimal partition, right? In each case that minimizes the correlation between each site. And when we do that, you see that, okay, the physical ordering is the appropriate one for the local system. The monomapped one is appropriate for the non-local system. And then at S equals 0, there's really not an appropriate sense of locality. There's not really a sense of locality. Okay, so just to go over, we showed that we can generate Hamiltonians with sort of arbitrary control over the distances at which interactions are happening. We can use that to generate different geometries and then reconstruct them. And then we also probed some sort of more exotic gravitationally inspired twin models. So in terms of what's next, we can imagine looking at sort of frustrated systems by changing signs, maybe solving some optimization problems, changing phases to study sort of topological physics, sort of starting to prove entanglement to generate sort of interesting states for quantum enhanced sensing. And in terms of gravity, we want to maybe look at dynamics and sort of start to probe the scrambling or some of the other ideas that people have. And also we're really excited to talk to everyone about any ideas you might have. And obviously none of this work is possible without everyone here. In particular, Philip and Eric work with me. We're all working together in the lab. And nothing's possible without Monica. And then this experiment was built by Emily and Greg. Yeah.
Let's thank Avikar then. Thank you. I mean, since we started 5 minutes after the hour, we still have time for, let's say, a few questions. So if somebody wants to ask Avikar.
Avikar, super nice talk. Just one very quick question. So at the end, you mentioned that you were looking at bipartite correlations. I was wondering, I guess, two related things. One, what specifically did you mean by bipartite correlations? And two, whether or not those bipartite correlations kind of one more or less expects to capture the right features of entanglement or other more complicated correlation functions that one wants to use to study scrambling?
So it's really simple. We're just cutting the system in half and treating each half, like averaging each half and looking at the correlations there. I guess our initial thought was, well, with these classical spins, can we measure maybe like mutual information, which would sort of be a classical analog to entanglement entropy? But I think basically the amount of data we'd need is sort of extremely large to be able to say things clearly which is why we're using this metric. I guess I haven't thought in particular about sort of other operators for probing scrambling.
I have a quick question. So when you draw the p-adic tree, like that kind of, I mean, like, do you mean like you can control? Well, I guess like in this case, I have 0 to 6 and then 1 to 7. So if you have an 8, you're going to have 2 to 8. Is that the case?
Yeah. So we always have a power of 2 number of sites.
So okay, so you take a 2 to the n sites, and then you can always find a way so that you only have coupling between the 2 to the m sites.
Yeah, exactly. Where m is like less than n.
Okay. Thanks.
So any more quick questions for Avikar?
Can I make a quick sort of, I don't know, comment to Norm's question? I think one thing we would love to do anyway for other reasons in this system is look at sort of like squeezing type inequalities to say something about entanglement between the modes. I guess one question for a theorist might be like, is there a way to connect that to things you prefer to think about, like entanglement entropy or to the scrambling? There is definitely some work from Anna Maria Ray, I think, looking at fluctuations actually as a measure of scrambling. So maybe that's something we should look back at. But the sort of easiest things for us to measure are fluctuations of kind of different spin coordinates on each site. And yeah,
got it. Very cool. Yeah, no, that's an interesting idea.
So if there are no more questions, let us thank Avikar again. Thank you, Avikar.